Have you ever thought about what would happen if the sun exploded? What sort of matter will it spew from its scorching core, and how will it impact our world? Alright, so some scientists are sounding the alarm on a so-called solar superstorm that could, underline the word could, eventually wipe out the internet for weeks or even months. These are big questions that have never been answered until now. You see, the sun's always undergoing tiny explosions on its surface. There was a solar flare, okay? We're approaching solar max around now, and there's some lead-up time to that. The sun is a turbulent, gurgling, boiling, roiling place, and part of that explosive energy often reaches our Earth, causing fascinating phenomena like the auroras we see in Scandinavia and much more. The plasma-charged particles see Earth's magnetic field, split, and then collide with our atmosphere, rendering it aglow when you get the northern lights. Every time you see the northern lights, we have just been slammed by a plasma pie from the sun. However, according to Neil, this time it'll be different as the solar flare just released by the sun is equivalent to 1 billion atom bombs exploding all at the same time. Join us as we learn more about these solar flares and how our Earth will change. Solar flare. First of all, you have to understand that these solar flares aren't some mysterious forces that just get spawned in space. These are natural phenomena originating from the sun's corona, and they are the cause of these incredible sights. The corona is the outermost layer of the sun, and these flares that are produced on the surface of the sun happen primarily due to the magnetic field of the scorching ball of fire at the center of our solar system. The thing about these magnetic fields is that they can twist and snap. When they snap, they release a large amount of energy that can literally burn our entire planet to a crisp. This is because solar flares can heat any atmosphere they touch to millions of degrees. When that happens, the particles in that heated atmosphere are charged up. As the particles get charged, the electrons and protons convert this magnetic energy into kinetic and thermal energy. The result is an extremely dangerous burst of X-rays and plasma that can create solar flares. The plasma created by these solar flares has particles that carry so much energy that they are accelerated nearly to the speed of light. The reason why Earth has been protected so far is that these flares don't occur in every region of our giant star. These flares actually occur in very specific parts of our sun known as active regions and are a temporary feature in the sun's atmosphere. Characterized by a very strong magnetic field, they are the most common source of violent eruptions such as coronal mass ejections, which are also known as solar flares. However, they aren't the only thing we should be worried about when it comes to our sun because there are other phenomena that can cause far more damage to our planet as well. A prime example of this is flare sprays, which can speed up eruptive material so fast it can reach velocities of 2,000 kilometers per second. The good thing is that the frequency of these solar flares is very inconsistent and can typically range from several times per day to less than one per week, making them somewhat less of a threat. We don't really know when solar flares are more likely to occur, but we do know there are certain types of solar flares, such as the X1 class flares, that can occur on average 8 times in the 11-year solar cycle. Then there are the minor flares like the ones belonging to the M1 class that occur around 2,000 times per solar cycle. We say solar cycle this, solar cycle that, but what does a solar cycle actually mean? Well, we're glad you asked. The solar cycle is basically the change observed in the sun's activity, measured in terms of the number of sunspots that have been seen over 11 years on the sun's surface. Bringing the conversation back, it's crucial to know that there are a lot more types of solar flares, different from the M1s and X1s we talked about. This type is known for emitting gamma rays, and it's no surprise that they're one of the most dangerous ones for this very reason. Understanding these distinctions is incredibly crucial because it helps us grasp the varying impacts of these solar flares. Talking about impacts, did you know the duration of these solar flares also varies significantly? Although the duration of these solar flares depends heavily on the type of electromagnetic radiation that's being produced by the flare, we use it to measure the electromagnetic radiation and then calculate the wavelength. This is important because different wavelengths are emitted through different processes on the sun's surface. Nonetheless, we discovered a very clean method of calculating the duration of a solar flare by simply measuring the full width of soft X-ray flux within specific wavelength bands. We found that the duration of a flare can be between tens of seconds to several hours, although this depends on the sunspot assumed to produce the flare. When the results were averaged out, we found that almost every solar flare will last between 6 to 11 minutes. This begs the question, can anyone with a telescope at home just start looking at the sun and counting the sunspots on their own? The answer is no, and we highly advise against it as there's a good chance you'll damage your own eyes. Agencies like NASA and NOAA make sure they monitor solar activity and predict solar flares. There are times when solar flares are more common. For example, if you look at the solar cycle, there's a period marked as a solar maximum and a solar minimum. These periods can be found at specific times in the 11-year solar cycle. During a solar maximum, there's an abundance of sunspots and heightened solar activity, meaning a greater chance that solar flares will hit Earth. The vice versa happens during the solar minimum period, where little to no solar flares are produced. Now, let's get back to NASA and NOAA because these agencies have proper satellites, such as the Solar Dynamics Observatory, constantly monitoring the solar activity on the sun's surface. Through these technological advancements, we can learn about the flares occurring on the sun's surface in real time. NOAA's Space Weather Prediction Center also provides forecasts processed by supercomputers, making them quite accurate. The question that should be cropping up in your mind right now is how these agencies protect their satellites. Considering how dangerous these solar flares are, how are the satellites able to function? Well, protecting the satellite is crucial, especially if they're going to record data from the sun. They were built using hardened electronics and redundant systems. We don't know a lot about these protective systems, but we know they use aluminum to protect their electronic systems. Let's get back to the issue at hand. Did you know that on December 14, 2023, the sun experienced a major solar event? While we on Earth couldn't notice anything with the naked eye, it emitted a massive solar flare, one of the biggest ever observed. It was classified as X2.8, and just to remind you, X class is given to the most dangerous solar flares. The figure of X2.8 means the solar flare's energy was almost 3 times more than the base level X1 flare. To understand how dangerous this solar flare actually is, imagine a billion hydrogen bombs, not atomic hydrogen bombs, going off at the same time. What will be the consequences of this solar flare on Earth, and can we even survive the complications? One thing's for sure, it's not something we can ignore. Solar flares this potent will have far-reaching consequences. For starters, forget about the functionality of the satellites in orbit around our planet, because the radiation will definitely fry up every system on these satellites. Secondly, forget about the radio because it will directly impact radio communications on Earth. There are even more dangerous complications, like potential changes in the Earth's ionosphere. What's the ionosphere? It's part of the Earth's upper atmosphere where extreme ultraviolet radiations and extrasolar radiations ionize various atoms and molecules, creating a layer of electrons. It's a crucial part of our atmosphere as it reflects and modifies various radio waves used for communication and navigation. If the solar flare that just happened on the sun reaches our planet, it can destroy GPS and other navigation systems we use on Earth. This solar event was monitored by many space agencies, including NASA's Solar Dynamics Observatory. There's a silver lining, too. As this was the most important solar event in a long time, it will provide us with a lot of data to predict future solar flares. Even though we have some technology for these predictions, we're currently unable to protect ourselves from these dangerous solar flares and could use a better system. The damage caused by the December 14th flare was quite immense, but we got off easy because the immediate impact was only on our radio communications. As explained, solar flares have the ability to emit intense energies of electromagnetic nature. This can easily ionize the upper atmosphere, causing disruptions in the radio signals that travel through that layer, leading to interruptions in your favorite radio programs. Show radio disruptions. Now, even though we make it sound like it wasn't a big deal, it did have a lot of effects on various industries that heavily depend on radio communication. For instance, communication and aviation departments and marine departments got disrupted a lot because they depended heavily on high-frequency band radio communication. The worst part about these disruptions is that we don't know how long they will last. Sometimes they can last for minutes, and other times they can go on for hours. That's not all, though, because these solar flares also have the potential to damage important satellites that are crucial to telecommunication departments. The damage, however, isn't just limited to these telecommunication satellites. They also affect geostationary satellites, although this depends on the intensity and duration of the flare that hit it. Damage to any type of geostationary satellite will result in the loss of functionality of navigational programs. Then there's the effect on Earth's power grids, because you do understand that electromagnetic energy is very much related to electricity that travels in the power lines above your houses, right? Physics can be funny like that. So, these solar flares basically have the ability to cut out the power for an entire city. They do this by creating electrical currents within the Earth's atmosphere itself, especially in the magnetosphere and the ionosphere. Now, these currents that have been generated in Earth's atmosphere find their way into your power stations. They travel in the power lines and, as a result, they trip up various systems that are placed to make sure that everything runs smoothly in the case of a power outage. The thing is, though, we knew of this possibility, which is why modern power grids have been made in a way that ensures these solar flares can't trip the systems causing power outages. However, intense solar flares like the X2-8 are very highly energized solar flares, and it can be a very difficult challenge for these modern power grids to hold the fort down on their own. It's not all bad, though, because stronger solar flares mean better quality auroras, or northern lights, and oftentimes these auroras are also noticed in lower latitudes. It can be a visual treat for those who are ready to appreciate nature's beauty. Now let's talk about the satellite that's responsible for providing us with literally every piece of information we have today about the Sun. The Solar Dynamics Observatory is a satellite that was launched on February 11, 2010, and was part of the Living with a Star program. It was installed with 3 essential instruments, each more important than the other one. The first instrument installed on this satellite was the helioseismic and magnetic imager. The job of this instrument was to study the solar variability as well as learn about the various components of the magnetic activity that's taking place in the Sun's interior. The next instrument was the Extreme Ultraviolet Variability Measuring Device, and its job is to measure the extreme ultraviolet radiation with improved spectral resolution. The third instrument installed on the satellite was the Atmospheric Imaging Assembly. It was developed by the Lockheed Martin Solar and Astrophysics Laboratory. This instrument performed a crucial job because it provided continuous full-disk observations of the solar chromosphere and corona in 7 extreme ultraviolet channels. It recorded data in very hot zones of the Sun, often working in temperatures ranging from approximately 20,000 Kelvin to more than 20 million Kelvin. This is definitely not the first time Earth has been hit with a solar flare. If we look at our history, the most prominent event regarding solar flares is the Carrington event. The Carrington event was basically the most intense geomagnetic storm in our history, or rather well-recorded history. Who knows, maybe solar flares used to be something that happened quite commonly in prehistoric times. However, let's talk about the most intensive geomagnetic storm in history. The Carrington event took place in September 1859, and it created extremely strong auroras all over the world. Now, as beautiful as that sounds, in actuality, it was a very big problem because it caused sparkings as well as fires in many telegraph stations. The geomagnetic storm was so intense that it was thought to be the result of a coronal mass ejection directly interacting with the Earth's magnetosphere. The scientists who recorded it were renowned astronomers Christopher Carrington and Richard Hodgson. Back in those days, the damage was somewhat manageable because the industries didn't really depend on electricity since everything was gas-powered. However, if something of the sort happened today, many things would be damaged. This is because nowadays everything is powered by electricity, and a solar flare like the Carrington event could cause blackouts as well as permanent damage for extended periods of time. The event was so significant that auroras were seen in every part of the world. For example, in the Rocky Mountains of the United States, where the possibility of auroras is slim to none, nevertheless, the aurora borealis noticed over this region was so bright that the gold miners thought that it was morning already. They woke up and even started preparing for breakfast. Similarly, in the northeastern part of the United States, people reported that they were able to read newspapers at night because of the aurora light. As we mentioned, the auroras were seen all over the world, and so similar reports came from Japan, Mexico, Cuba, Hawaii, and China. Even the countries that were close to the equator, like Colombia, weren't spared. It was a different story for telegraph operators, though, because they suffered a lot from the geomagnetically induced current from the electromagnetic field of the auroras. Telegraph systems all over Europe and North America failed miserably, and the operators were also getting electrocuted. It was a chaotic scenario, to say the least. Everything was sparking up. Telegraph pylons were spewing sparks, power inlets were spewing sparks, and just about everything that functioned electrically was either burned or not doing its job properly. Some operators were able to send and receive messages without even connecting the machines to power supplies. For example, two operators, one working in Boston and the other one in Portland, were chatting with each other using the auroral currents. This happened on September 2nd, 1859, and the conversation is recorded. In the conversation, you can clearly read that they're talking about disconnecting their telegraph machines, while one of the operators in Boston even complained that the current is very strong at times. Isn't that amazing? What's surprising is that the conversation lasted for more than 2 hours without using any battery power at all, working solely with the current that was induced by the aurora. This wasn't the only event that took place in our history, because if you look back into our past just 35 years ago, on March 13, 1989, a geomagnetic storm struck the Earth. It was a very strong solar flare that hit our planet, and it caused a very serious 9-hour outage of Hydro-Quebec's electrical transmission system. The onset time was extremely rapid, and according to various astronomers, this geomagnetic storm resulted because of 2 coronal mass ejections. Even though the auroras weren't seen all over the world, they were quite noticeable in the states of Texas and Florida. Now, everything was fine until the people started panicking, because this event took place when the Cold War was going on between the Americans and the Russians, and so a lot of people thought that a nuclear strike might be in progress. However, the more knowledgeable civilians thought that this might be related to the Space Shuttle mission STS-29, which was also launched on March 13, 1989. In modern times, the most dangerous solar storm happened just 20 years ago. It was dubbed the Halloween solar storm. It was basically a series of solar storms that involved solar flares as well as coronal mass ejections. These solar storms lasted from mid-October to early November, and the series of storms generated were the biggest that were ever recorded by the GOES system. The GOES system is an acronym for the word Geostationary Operational Environmental Satellite, and it's operated by the United States National Oceanic Atmospheric Administration, otherwise known as NOAA. The effects of these Halloween solar storms in 2003 were quite massive, because on Earth, a lot of satellite-based systems as well as communication were affected. We're talking about aircraft damages and hour-long power outages in Sweden. The storm was so significant that 12 transformers had to be replaced in South Africa, which is a country that has an incredibly low geomagnetic latitude. In space, the Solar and Heliospheric Observatory was disrupted. It was manufactured by the European Space Agency and launched on December 2, 1995, in order to study the Sun. Almost all of its communications were cut off, and the Advanced Composition Explorer was also damaged. The astronauts who were in space aboard the International Space Station were advised to stay in the more shielded parts of their station. These parts were called the Russian orbital segment, and they were asked to wear protective gear so that they are safe against the increased radiation levels. Now, even though we know a lot about our own solar system and how these solar flares work, we still don't know everything. This is why it's important that we look into other solar systems around our galaxy and try to understand and learn more about solar flare activity. Recently, research has pointed out a very interesting star known as TRAPPIST-1. We say interesting because it's a red star that's much smaller when compared to our Sun. Its temperature is also lower, measuring at about 2,566 Kelvin, which is almost 2,300 degrees Celsius. Still, it's not as small as our Moon, and it's still slightly larger than Jupiter. If you compare the Sun and TRAPPIST-1 side by side, it has a mass of about 9% when compared to the Sun. It's definitely older than our solar system, and the discovery of this star was first published in 2000. The amazing thing about this star is that it also has a solar system much like ours. Although there's a difference between our solar system and the one we are interested in, our solar system has about 8 planets, while this one has 7. Unlike our year, which takes 365 days to complete, it takes only 1.5 to 9.18 days for the planets of this solar system to orbit completely around the star. The planets don't have a day and night like our Earth. While they each orbit around the star, they are tidally locked to it, meaning that one side of the planet always faces the star, causing permanent day on one side and permanent night on the other. Now, we all know the question that's popping up in everyone's brain. Is life possible on these planets? Well, We did our due diligence in finding out everything about these planets, and unfortunately, we'd like to report that there's no life possible on these planets. This is because there's no evidence of any type of atmosphere on any of the planets. Even if there was an atmosphere, the planets that revolve around this star are full of volatile chemical elements, meaning everywhere you step, there will be chemicals that are constantly being vaporized, and who knows what you might inhale when you're on those planets. So, it's best we leave them. Still, up to 4 planets that have been designated as D, E, F, and G are at appropriate distances from the star, meaning that the temperatures on these planets are appropriate for human life to thrive. Now that some of your most burning questions have been answered, let's talk about the significant stellar activities of this star. Did you know that this star, even though it is cooler than our Sun, produces intense solar flares that are much more violent than the ones produced by our Sun? Now, you might be wondering, how did we record and learn about these solar flares, especially when the star is approximately 40 light-years away from our planet? This is where the James Webb Space Telescope comes in because it's been instrumental in observing these flares. The sophisticated infrared capabilities of this satellite can be used to detect various details that were previously invisible. The James Webb Telescope has identified 4 types of solar flares from this mysterious star, and each one of these solar flares is much stronger than what we usually face on Earth. This means that our survival on the planets surrounding the star is not going to be as easy as we thought. Now, even though we've studied a lot of other planets and their stars, our current methods of flare prediction present some problems. For one, we don't have any type of indicators that can provide us with accurate information regarding the future of flares, so we still can't predict which active region on the Sun will produce a flare. This doesn't mean that our knowledge of sunspots and active regions is of no use. On the contrary, the information we've received from various satellites does help us. For example, we found that magnetically complex regions on the Sun are called delta spots, and these spots are likely to produce the largest flares. We've even developed a simple scheme of sunspot classification so that, based on the energy levels of a particular sunspot, we can find out the probability of occurrence for flares in the M or X class within 24 to 48 hours. Stay curious and keep your eyes peeled towards the stars. See you next time.